In this video, we explore momentum and impulse a little bit further, especially in the way IB physics looks at momentum and impulse. The three aspects that we're going to look at in this video are force time graphs. In the IB curriculum, we look at a lot of graphs, probably because it's supposed to be a lot more experimental than what we do in honors physics. So here we're going to look at force time graphs and what the area or the slope, in this case primarily the area, what does that mean? Then we're also going to look at situations where mass is not constant. This is the situation when we have rockets or water jets. The last thing I'm going to add is a little short discussion on the center of mass and how we can use the center of mass to do some calculations with respect to conservation of momentum. Okay, first off, when force is not constant, okay, so force is going to be a function of time, then impulse cannot be calculated simply by saying impulse is equal to force times time, because your force isn't constant. Okay, instead, if you can graph it, okay, then we can use the force time graph, and the area under the curve, okay, the green area in this case, would represent the impulse. Okay, from a calculus standpoint, okay, you have to understand that the impulse is going to be the integral of the force with respect to time. When you get to that in the calculus area, hopefully that'll make more sense. Okay, but for now, what we're going to do is represent the area under the curve either geometrically. In this case, it's a triangle, so 1/2 base times height. Or as we move, you may need to approximate it as a geometrical shape. Okay. So if, however, you don't have a force time graph, but you have a acceleration time graph, okay, remember the area under the curve of an acceleration time graph is the change in the object's velocity. So therefore, if I have mass, it ends up being the same thing. Mass times the change in the velocity. Mass times the acceleration gives me the force. Okay, so for example, I have a, this is example 2.49 in the textbook, and here I have a ball of mass 0.20 kilograms moving at 3.6 meters per second on a horizontal floor, and it collides with a wall. Okay, as a result, it bounces back at a speed of 3.2 meters per second. So yes, it does lose some energy in the collision, as you would expect. Okay, the ball was in contact with the wall for 12.5 milliseconds. Determine the maximum force exerted on the ball, assuming that the force depends on time according to the following graph. And this kind of shape for a collision is not uncommon, okay? It's a kind of an elastic spring-like collision on the way in, and that's the upward slope. And then on the way away from the wall, it releases the energy of that spring, and so you get much of that energy back. Okay, so in this case, we do need to know, okay, information. I have no units on my graph. However, I do know the ball was in contact with the wall for 12.5 milliseconds. So that's the base of my triangle. The height of my triangle corresponds to that maximum force. So if I do the area of a triangle, 1/2 base times height, and fill in the various values and the variable for the maximum force, I can calculate that the impulse is going to equal that 1/2 0.0125 seconds times F max. And I also know impulse is the change in my momentum. So I start final minus initial, calling away from the wall positive. I have the mass of 0.2 kilograms. So here's my 0.2. Okay, times the velocity away, positive, minus, okay, and here's the vector nature of my velocity, remember. Okay, the negative 3.6 as I'm moving towards the wall. So I declared away from the wall to be positive, towards the wall is therefore negative. Okay, you put this all together, do the calculations, and you find that the maximum force exerted by the wall is 220 newtons. Okay. So what happens when the mass is not going to be constant? Okay, usually the mass is constant, the ball doesn't change. Its mass after it bounces, the object's really don't change much as a result. Okay, but there are situations where water is being added or water is leaving an object, or in the case of a rocket, it expels hot gases out the back, and as a result, it moves forward. Okay, so when mass is not constant, I have to look back at the origin of my equation. Okay, in this case, primarily the origin of Newton's second law that says my force is equal to the change in my momentum with respect to time, okay, or the rate of change of my momentum. Well, momentum has two components, mass and velocity. Okay, normally it's the mass that stays constant and velocity is a function of time. However, it could be the other way around, okay? My mass could be a function of time and my velocity stays constant. Okay, so either way, the impulse, okay, going the other way, my impulse is going to be the integral of force with respect to time, that area under the curve, or change in momentum. Okay, so if I look at it as a change in mass, I have to pay attention to the rate of change of my mass, okay, because that's going to correspond to the rate of change of my momentum. Okay, so for example, I have a cart moving in a horizontal line. Okay, it's got a constant speed v, so I can breathe a sigh of relief. I don't have to worry about the v. Okay, and rain starts to fall and the cart fills with water at a rate of sigma kilograms per second. Okay, that little figure is lowercase sigma. So here's another Greek letter that we've learned. But in 1 second, I basically have added sigma kilograms to my cart. Okay, and the cart must keep moving at constant speed. It's on an assembly line, you know, just because it's raining can't slow things down. So I need to apply a greater force to keep this cart moving. Okay, so since that force that I need to apply corresponds to the change in my momentum, rate of change of my momentum, after I go through the various formulas and algebraic manipulations, I find out that this force is simply going to equal that rate of change, sigma, okay, times the constant velocity. Okay? So that's going to be important because rockets and jet engines operate by conservation of momentum. What happens is to get the object, there's nothing to push off of in space or out in air other than the air. So what happens is that in rockets and jet engines, the engine basically shoots something out the back. For a rocket, it's basically rocket fuel, okay? For a jet engine, it's air. But it goes out at a very high speed, okay? Usually, you know, hundreds, maybe thousands or greater meters per second, okay? And by conservation of momentum, the air or the rocket fuel had its momentum changed because it was at rest, and now it's going at hundreds of meters per second. And by conservation of momentum, the jet or the rocket must go forward a similar change in momentum. The force that the jet puts it on the air equals the force that the air pushes on the jet. Okay, so those two formulas, okay, in terms of conservation of momentum, and we can therefore calculate, if I know how much mass and how much, what the velocity of that rocket fuel is, I can then calculate how much force or what the change in momentum of my rocket happens to be. Okay. In reality, the rocket fuel equation is a little more complicated because as the rocket uses up that fuel, the mass of the rocket decreases. Okay, so we would need to get a little more complicated in our calculus to calculate it, but for now, we are pretty much going to assume that the change in mass of the rocket or jet is fairly negligible. So, for example, I have a rocket in space far away from any planetary mass. That just means I can ignore gravity. Okay, it uses newer ion propulsion engines that eject xenon ions instead of chemical rocket fuel. Okay, the ions leave the rocket at a very high speed, okay, 5,000 meters per second. or 5 kilometers per second. Okay, but very little mass goes out the back. Okay, 1 milligram. So calculate the average force on the rocket. Okay, so yes, the rocket is providing a force on the xenon ions, and by Newton's third law, the xenon ions provide a force on the rocket. And I can calculate that using the change in mass rate equation, okay? Because the force on the rocket, on the xenon ions, is going to equal the rate of change of the mass times the speed that that mass goes out at, okay? Or basically converting the mass rate to kilograms per second, not grams per second, okay, but kilograms per second. 1 milligram turns out to be 1 times 10 to the minus 6 kilograms per second times the speed that it goes out at. And so the force that I experience is not a lot, okay, I admit that, okay, it's 5 times 10 to the minus 3rd newtons, or 5 millinewtons. But when I apply that over a long period of time, yes, that acceleration on my rocket adds up. So an alternate approach that you can take upon on this is basically saying how much mass leaves my rocket in 1 second and what is the velocity of that mass. Okay, you use that value of 1 second because that's the number that we use under the bottom, okay? The delta t, if delta t is 1, I can pretty much ignore it, okay? It's factored in, okay? So since my delta t is 1 second, the formula just becomes mv of the ejected mass. Okay, so I shouldn't say equals, I guess it's equivalent to, because the units don't add up. But in this case, all I have to do is take my mass, which is 1 milligram, or 1 times 10 to the minus 6 kilograms, times that velocity, 5 times 10 to the third, and I would get the same number. Okay, I want to talk a little bit about conservation of mass because the conservation of mass can show up in this unit a little bit. Conservation of momentum. So the conservation of momentum for multiple objects, okay, as long as it's a closed system, remember a closed system has no external forces, okay, all of the forces are internal. If it's a closed system, I can treat it as one object. Okay, and that one object has a center of mass associated with it. And because it's one object, even if that one object is moving, okay, then that one object would have a momentum associated with the center of mass. So, the center, how do I calculate the center of mass? Okay, the center of mass is basically taking one of the masses and multiplying it from its distance from the center of mass, and the other object times basically its distance from the center of mass. Okay, so m1 delta x1 equals m2 delta x2. Okay, kind of think of it as a balanced seesaw type of situation, where delta x1 and delta x2 are the distances. So for example, I have a 20 kilogram boy stands on one end of a 2 meter long plank that has a weight of 100 newtons. Okay, the plank, because it's a uniform plank, we assume that, the center of mass is just going to be exactly in the middle. Okay, the boy we're going to treat as a point particle, and so we're going to call him 20 kilograms at x equals 0. Okay, meanwhile, the plank has a 10 kilogram mass, and we put that right in the middle, x equals 1 meter. So balancing the equation, we basically say, well, 20 times c minus 0, okay, delta, his distance to the center of mass, is going to equal 10 times 1 minus c. Okay, c is basically the location of the center of mass. After some algebra, we find that the c, or the center of mass, is it's pretty close to the boy, as you would expect, because the boy balances off, okay, somewhere around here, okay, around a third of the way. So how would I use that? Okay, if it's a closed system, no external forces, okay, in this case, the boy stands on one end of the plank. The plank is on ice, and friction between the plank and ice is negligible. By eliminating friction, I basically said this is now a closed system. Okay, the boy walks to the other end of the plank. Okay, and how far does the boy walk? just glance at it, you would think, okay, he walked to the end of the plank. It's a 2 meter long plank. It's easy. He walks 2 meters. Unfortunately, as he walks forward, okay, he applies a backwards force to the plank, okay, because of Newton's third law. The reason he moves forward is because the plank pushes him forward, and in return, he pushes the plank backwards. Okay, so he does not walk 2 meters. Instead, because we can ignore all the external forces, we can treat it as a system. And as a system, there is no external force. Okay, if there was an external force, then that would be an impulse into my system, but there isn't any. So basically, my center of mass never moves. Okay, so it's at x equals 0.33, and it stays at x equals 0.33 as he walks this entire time. Okay, so by symmetry, as he walks, at the end, when he gets to the end of the plank, okay, it will be 0.33 meters from the right end of the plank. Okay, so let's draw what that looks like or animate that as he walks across. What does that look like? Okay, basically he walks forward to the end of the plank, and now the center of mass is 0.33 meters from the end of the plank. And if you look at it, it means the boy only walked 0.66 meters. Okay, and that's how we can, if we can imagine the center of mass and the fact that the center of mass as a system, okay, doesn't really change, okay, then for a closed system, it never moves, and for a non-closed system, the external forces, okay, would basically act as an impulse on the system. Thank you.